we are going to work problem number 1998 from the buffer free response questions, page 3. And this has important information that has really nothing to do with buffering, but everything to do with acid-base titration, which will be on this 2020 exam. And so this is a common practice that we did not get to do, and so we're going to walk through it together now. So it says approximately a 0.1 molar solution, it's approximate, of NaOH is to be standardized by titration. What does this mean? To standardize it means to determine its exact concentration. Okay, so that's why it says it's approximately. Assume the following materials are available. Okay, so briefly, what we have is this pure solid acid called KHP. This is a monoprotic acid, so it's really like HA. So it's only going to give away its one hydrogen, and it's going to be what's called a primary standard. Why is this? Because this pure solid can be taken out of the little jar. You can dry it and mass it, get the grams of KHP, use the molar mass of KHP, and determine exactly how many moles of it you have. Okay, so you know exactly the moles of H plus you're going to have. And you just put it in enough water to dissolve it. It doesn't matter the concentration. It only matters the moles of this, because if you have, say, 6 moles of H plus, whether you put it in 50 milliliters or 100 milliliters, you're still going to have those 6 moles. And as soon as the hydroxide ion that you put in, it is going to react with each one of those, and it's going to neutralize them drip by drip by drip. So this is coming in through the burette, so you would know exactly the volume of the OH minus you put in, and you would know mole for mole. You knew exactly how many moles of acid you put in, and at the equivalence point, moles acid equals moles base. And so if you know the volume that you put in, then you would know at the equivalence point the moles of base you put in, and then you could find out the exact molarity. So it wouldn't matter how much, what the concentration, how many liters you put it in. You just put it in enough water to dissolve it, but you know exactly how many moles. How is this different? Usually we get a volume and a concentration of something that's going to go of what we're going to titrate against. So here, and what do we do with that? We just take it to moles, right? That's what we're always really looking for. And so here, we just get to skip that step. Okay, so one of the things that we do is you take this dry, solid acid, and you're going to take its mass. So it says, describe briefly the steps you would take using the materials listed above to standardize the NaOH solution. So your first step is to record the mass of you want to get it as precise as you can, and you're going to mass that and dissolve it in water. So we're going to use this analytical balance to record the mass of this, and we're going to dissolve it in, we should say, distilled water. And then they even gave us the hint, here we're going to have to add our indicator. So we're going to add phenolphthalein as our indicator to be our indicator. And then we're going to rinse our burette. This is always important. They always ask you this. You're going to rinse your burette with your titrant. What are you going to be putting in there? Your OH minus. And so you're going to rinse the burette with your approximate 0.1 molar NaOH. And then you're going to, so this is always important. We're never going to rinse with distilled water because some of the water could be left in the sides and dilute the titrant we put in, the NaOH we put in there. And then we're going to fill the burette with that 0.1 molar NaOH. And, oh, I'm sorry about this. You need to do this twice. You need to rinse twice. And then you're going to dropwise add the NaOH to your KHP solution. Oh, dang it, I forgot. See, I would have lost all my points here. Record your starting volume. Okay, so you've got to record your mass and record your starting volume. Then, that's of your NaOH. Okay, so then you're going to add dropwise until the solution turns light pink. That is going to be your end point, where your indicator changes color. And then if you've done a good job, that should be your equivalence point. If you've done a good job of picking a good indicator. Okay, then you're going to record, I want that dark color, record your final volume of NaOH. So you know exactly how much you put in there. And then for good measure, you're going to repeat the process to check your results. Okay, B says, so that's just the process of the titration. Okay, so you're going to start off with this solid KHP, and you're going to take its mass and you're going to record that mass. And then you're going to add phenolphthalein to it because you have to have a way to know when you get to your end point. You're going to rinse that burette twice with your titrant, which is the 0.1 molar NaOH. And then you're going to fill that burette and you've got to record your initial volume. You're going to drop it until you reach the end point, which is where the color changes, and record that final volume of the sodium hydroxide. B says, what calculations would you do? The setups would be necessary to determine the concentration. Okay, so B, first you're going to find moles of KHP. And so you've got grams. So you're going to take your grams of KHP and you're going to multiply it by grams of KHP in 1 mole of KHP. And that's going to give you moles of KHP. Okay. Secondly, at the equivalence point, always put this in there somewhere. We'll write out the word equivalence point. Always write this in there. Moles of acid equal moles of base. Moles acid equals moles base. So, now, what volume? You need the volume of base added. At the equivalence point. So that's always your final volume minus your initial volume. But you know, burettes usually read down, and so it's going to tell you basically how much you put in there. And that's going to be the volume of NaOH added. So then you have, since moles of the acid equal moles of base, therefore the moles of your acid divided by the volume of your base, and you could just put this as just as well if you put base here, divided by the volume of the base, but I've got to call this now. I need to be writing these. I need to say what this is. So therefore, moles of KHP. So this is at equivalence. Moles of KHP is equal to moles of NaOH. And then if we take moles of NaOH and divide it by the volume of NaOH added, we get the molarity of the NaOH. All right. So that's how we do that. Okay, a couple of important things. If you see this whole standardized, that means you're going to find out, determine the exact concentration. Almost and forever, it's done against this primary standard KHP. It's a pure solid if they ask you. So one of the things maybe you need to know is that when you have NaOH in a jar, as soon as you take out, they come in little pellets. As soon as they hit the moisture in the air, they start absorbing water. So there's no way, even if you put them in a drying oven, which we would do with this pure solid, the KHP, it's not hygroscopic. This is, and so it would starts absorbing water from the atmosphere immediately. So any mass that you have is automatically got an error in it, because you're having NaOH plus whatever water is on there. So that's a source of error they could ask you about. And so in order to get an exact concentration for hydroxide, especially sodium hydroxide or potassium hydroxide, you have to titrate it against a known primary standard like KHP. Okay, so again, we're going to mass it, record that mass, because we're going to be able to have to take that mass and figure out how many moles. Then we're going to add our phenolphthalein. Don't forget this, otherwise you have zero way of knowing when it changes color. You got a test coming. And you're going to rinse that burette twice. You're going to fill it with the sodium hydroxide, record that starting volume. You're going to drop it, you're going to add the hydroxide dropwise to the acid solution, KHP solution, until the solution turns light pink because you put phenolphthalein in there. So as soon as all of these are matched up and you have one extra drop of OH minus, that is going to take you to your pink color. Phenolphthalein is colorless in acids, but it is pink in bases. So as soon as you just pass, that's why we want it light pink, because if you put too much more, you would have an error. So if you overshot it, your volume would be measuring the extra OH minus you put past your equivalence point. I hope that makes sense. If you have a question about that, just ask me. Next part of this one. See how this has nothing to do with buffers, therefore we need to do it. Okay. All right. After the NaOH solution has been standardized, it is used to titrate. So we've got this known that we're doing. So we've got, this is going to titrate a weak acid. So we've got an invasion going on. Strong acid, strong base, weak acid. It's used to titrate this. The equivalence point is reached when 25 milliliters of of NaOH solution has been added. So what's in our beaker? HA. And we're dropping in OH minus. Okay, in the space provided to the right, sketch a titration curve showing the pH changes that would occur as the volume of NaOH solution added increases from 0 to 35 milliliters. Clearly label the equivalence point. Okay, let's just think about this for a second. All right, so if I mark this as 7, is the pH, is the equivalence point of this titration going to be at 7? No, that only happens with strong. Whoever's strong is going to win this race. So the pH is going to be basic. So this says to 0 to 35 milliliters. Okay. Okay, now, but it says the equivalence point is reached at 25. Oh goodness. Okay, I'm gonna back this up, and I'm gonna make this 40. So if I said 10, I need to find this line. Okay. So 20, 10, 30. And I'm going to be putting this much in. Okay, so I've got to come to this place. And the equivalence point occurs at 25 milliliters. So this is volume of NaOH added. And so at 25, so that's right here. Okay, so now I'm just going to dot this line. Okay, so now where should my equivalence point be? I remember that, okay, so I'm starting off with the weak acid, and I remember they do that little hump thing, short and stubby. That's probably too long. Okay, I remember that that's what, and I know this is a low pH, right? So I've got to start low, but I'm not going to start at 1 or 2. I'm going to start, this is halfway there is about 3.5, so I'm going to start about halfway to 7. And then I reach the equivalence point over here. Strong winds, so my equivalence point has to be greater than 7. So I'm going to make a short squatty thing. I'm just going to start this way. Like this, and I'm going to call this my equivalence point. We don't have any real numbers, right? Okay, so now I'm going to go like this and like this. And then, let's see, wait a minute. I need to make this taller. Yeah, it's going to finish strong. Okay. So I've clearly designated that, and I'm going to call this 12, because I don't want him to think it's 14. Or maybe I'll call it 13. Okay, and this will be about 4. All right, so it says, now, it says to 35 milliliters. I went past that 35. Okay. Label the equivalence point. So that is the equivalence point. I need to make that a lot better. Oh. So halfway here to here would be like this. And I'm going to call that the equivalence point. Okay, now, let's see if we got that right. Okay, so I'll clean that up a little bit, but something I did that was kind of foolish. This, I should clearly mark this line as 25 milliliters and not make anybody guess that. Okay, so there was a point for starting the pH below 7. There was a point for having the equivalence point at above 7 at 25 milliliters, and then for finishing off above a pH of 7. So we got all our 3 points. While they could have guessed because I did number these, it's all would have just been better if I had just full out labeled it. Okay, that 25. Okay, all right. So now I got to clean up this mess. Okay, next. Describe the value, how. See how these are like all conceptual? That's why we needed to work this, because you have to explain all this stuff, and that's what you're going to be doing on your test. All right. So, describe how the value of the Ka for the weak acid HX could be determined from the titration curve in part C. Okay, so how do you determine the Ka? That half equivalence point, don't ever forget this, that half equivalence point is where pH is equal to pKa, and all we got to do is take the negative exponent of that to get the Ka. So what is half of 25? About 12.5, so I'm going to call it about right here. And it just tells me to do that. So the half equivalence point. So at the half equivalence point, it says describe. At the half equivalence point, when 1/2 of the titrant, or what you can name it, whatever it is, 1/2 of the titrant needed to reach the equivalence point has been added. The HA, that's your weak acid, the concentration of weak acid is equal to its anion, the concentration of its anion. Since Ka is equal to H plus over A minus, over the concentration of HA. If these two things are equal, then Ka is equal to the hydrogen ion concentration, and pH is equal to the pKa. So that's how I could find it out. So I could take the negative log. Nah, I don't think I have to say all that. Let's see if we got... Okay, so it turns out we didn't have to define it. We just had to say, but I would. You want to go over the top. At the half equivalence point, pH is equal to pKa. And that, that was all we had to say. Okay, all right, so now the graph below shows the results obtained by titrating the weak acid H2Y with a standardized NaOH solution, with that standardized solution. Identify the negative ion is present at the highest concentration at the point of the titration represented by the letter A in the curve. Okay, letter A in the curve. Okay, so let's look what's happening. At the beginning down here, we have H2Y. That's all we have at the beginning, none added. And as we're doing this is a strong weak. So we got all this buffering back and forth. This is a buffer zone. And then halfway, this is your equivalence point, which means that you've used up all of your, so you got two dissociations, let's put it that way. And the first one's going to give you H plus HY minus. The second one, HY minus, is then going to release that, and you're going to get Y2 minus. So this is what happens at the first equivalence point, right? So you're knocking out all of these, okay? And so now you are getting rid of this. Does that make sense? So the first one goes at the first equivalence point. You've neutralized all of the first ones, and now you're working on neutralizing the second ones. So this is a buffer. So this equivalence point, because you see, like, these little things they're not very straight, but those are the straightest slopes of these strong weaks. And so that is the equivalence point. All right, so now it says, what is the strongest negative ion? Well, so what do you think? How about that one? Because this has been giving up these Y's, and we've been obliterating that, and so what is negative? So you could have some of these left, but what's going to be mostly there at the equivalence point? When moles acid equals moles base, your base has been obliterating all this. So Y2 minus. Okay, so this was for 1 point, and this was for 1 point. Okay, all right. So I think this was a very important one because you're using the fundamental parts of titration curves and standardizing acids and bases. Okay. All right, that does it for this one.